Next, we come to the concept of impulse. Impulse is written with an uppercase I, and it's the change in momentum. Okay, so not the rate of change, but just the change, delta P. And since delta P over delta T is equal to F, we have impulse as F times delta T. So maybe I'll write here that original equation so that you know impulse equals delta P. Okay. And if you divide both sides by delta T, this is going to become F. F times delta T is going to be impulse then. Okay. So what are the units? If we look at units for momentum, it's kg meters per second. So it's just a change in that. So it's going to be the same units as the momentum, kg meter per second. Now, okay. Impulse momentum theorem, we're just going to read it. The theorem states that the impulse acting on the object is equal to the change in momentum of the object. So it's basically the definition of impulse. Here it is again, right? And remember, whenever we're doing this, we're going to do final minus initial. Yeah? So final momentum minus initial momentum. It's also a vector quantity, so it's in the same direction as your vector subtraction of P final minus P initial. Yeah? So this doesn't have to be in the same direction as the momentum itself. In fact, mostly it won't be. If the force applied is not constant, you have to use the average applied force. Okay, so what does that mean? Here we have a force time diagram. And say I start pushing an object and I start slowly, then build up, and then I again, towards the end, push slowly. Then you would see this pattern for the magnitude of my force. Yeah, I start with a low force, my force peaks, and then it drops again to zero. Yeah, over time. So this is the initial time, this is the final time. So there's no one constant force here, there's no one number. But you're going to take this shaded area under the curve, make a rectangle whose height would be such that the area of this rectangle would equal the area under this curve. Then the height of that gives you the average force. Okay. You will not be asked to do this. You should simply understand this concept. You will only deal with cases where the force is constant. Okay. But you should understand how one finds the average force, which is equivalent when the force applied is not constant. Okay. So the impulse imparted to the force during a time interval delta t is equal to the area under the force time graph from the beginning to the end of the time interval, which is what we saw on the previous slide. Or the impulse is equal to the average force multiplied by the time interval, or delta P, which is same as impulse, equals F average times delta T. So we're just looking at the same definition, this time graphically. Now we come to how impulse is important for collisions. Basically, the most important factor in the collision is the time it takes for the person to come to a stop. Okay? The slower you can come to a stop, the less your acceleration, right? Because remember, acceleration is rate of change of velocity with time, okay? So the quicker your velocity changes, you come to a stop means velocity goes to zero, right? The quicker that changes, the greater the acceleration on the body. Acceleration is directly related to force, F equals m into a. So that means the greater the force on the body, the more likely that things will break, like your bones or whatever. I was recently rear-ended, and I have direct experience of this, unfortunately. Okay. So the ways the auto industry makes us safer are by increasing that time for your body to come to a stop. Okay. And one of those ways is by using the seatbelt. The seatbelt essentially straps you in with the seat, which means you cannot be thrown forward and hit the dashboard or any part of your vehicle, if you do that, if you hit any part of your vehicle, if you don't have a seatbelt, you are coming to a stop faster than your vehicle might come to a stop. So the seatbelt holds you and forces you to slow down to a stop at the same rate at which the vehicle slows down. Yeah. Also, so it's increased that time, delta t. Airbags also help to increase that time, because if the airbag deploys and it inflates, you hit the airbag and you slow down because it offers you a lot of resistance. Yeah? So you are now slowly coming to a stop rather than as fast as you would without it. So these two both use the increasing time. Of course, airbags also act in other ways. They cushion you and they spread out the area over which the force acts. So the pressure becomes much less. Okay, but here we are interested in that elongating that time to come to a stop. So you need to understand the relationship between the damage that happens to the body, which depends on the amount of force that is applied to the body. Force depends on acceleration. Acceleration is the rate of change of velocity. We're trying to lessen that acceleration. You're trying to slow down how quickly the velocity changes. Yeah? So let's look at a typical problem to get a feel for the numbers. Consider a 75 kg person traveling at 27 meters per second, which is same as 60 miles per hour, coming to a stop in 0.01 second. These are fairly typical values, okay? This is without a seatbelt. What is the force and what is the acceleration? So to get the force, we need the acceleration. Let's get the force from the change in momentum. You know, the final velocity is going to be 0, right? And we know force equals delta P over delta T, yeah? Delta P is mvf minus mvi, right, initial, over the time elapsed. Time elapsed just is 0.01 seconds. M is 75 kg, so you're going to put that in there. Your final velocity is 0 because you've come to a stop. Your initial velocity is this 27. You want to choose the MKS units 1, the meters per second. Now, if you put the values in, you should get a force of 10 to the power 5 magnitude, right? So 2 times 10 to the power 5 newtons. Here it's with a negative sign. The sign just tells you whether it's going to the left or the right. Here the sign is unimportant. We are interested in the magnitude, okay, the value of the force. So it's a pretty large force of the order of 10 to the power 5 newtons. And if you divide this by the mass, so F equals m into a, all right, let's write that down. So let's make that step a little more clear. If you want to now find the acceleration, you're going to use F equals m into a, or you're going to divide that force that you just got by the mass, which is 75 kgs, and that should give you 270 times g, which is 9.8, yeah? So that's to give you an idea of how many times the acceleration due to gravity your body has to take. 270 g. Okay, you might have heard of the term g-force. That means how many times g. It's a way it's a unit we like to use for acceleration. This is almost certainly fatal. I'm going to show you now what kind of g-forces your body is able to tolerate. Okay, in a minute, we'll come to that. So we looked at seatbelts and how they work, okay? And basically when you have a seatbelt, the new time to stop is about 0.15 seconds as opposed to unprotected, which we saw in the previous slide, 0.01 seconds. So it's at least a factor of 10 improvement, yeah? And the new force is about 9.8 times kilonewtons as opposed to 200 kilonewtons. So that's a factor of 10, yeah? 1 order of magnitude. Remember I said an order of magnitude is 1 factor of 10. Okay, so that's a huge change right there. 1 order of magnitude is quite a big change. You definitely need the seatbelt. Do not ever travel without the seatbelt, even if you're in the back seat or wherever. Okay. And we talked about the airbags increasing the time of collision, decreasing the pressure, and that's how they act. Okay. So here's a very famous man, John Stapp. He was an Air Force pilot, And he was very interested in these large accelerations and to study how much the body could withstand, whether you could train the body. And you indeed can train the body to withstand greater and greater levels of G-force. Here, he's doing one of his test experiments, and you can see how much his face the blood is rushing to his face, yeah? The G-force. He survived for a very short time at maximum force of 46 G, yeah? And that you can only take for a fraction of a second, okay? So I'm going to just let you read these. These pictures are taken from the Edwards Air Force Base. History of our bodies cannot take more than a couple of G, 2 to 3 G. Most of the fairground rides, they don't have G going any higher than that. You can tolerate about up to 10 G for 1 minute, okay? Up to 20 G for under 10 seconds, okay? After that, you're going to suffer severe consequences, if not it being fatal. And up to 25 G for 1.1 second. That's what he had, 25 G for 1.1 second. So how did he withstand up to 46 G, even for a fraction of a second? That you can improve your ability to withstand this with training. However, it does take a toll. I would not advise it, okay?